how can we be sure the predictions we get are accurate? So we're going to go and look at something called the Boston data set. And this is a famous data set. And incidentally, the original reason it was collected was something for which it failed miserably and wasn't used. They wanted that housing prices were related to chemical concentrations of some sort, but it wasn't. So the main difference is I'm going to use R, so you'll get a different feel for a different language. And as I said, we're going to use a data set called the Boston Housing Set, and it's information about housing prices. So there's 506 rows, which are 506 houses, with 14 columns information. So there's of information about each house. Actually, the rows correspond to an average for a district. And the most important thing is we want to see if we can use this data set to predict the median value of a house based on other variables. So one difference between R and Python that's important is indexing. Python uses zero indexing, and R uses indexing like mathematics. So as I say in this last thing, if I wanted to index an element that was in the second row in the fourth column, I would say Boston 2, 4. Is that going to work? Oops. And not Boston 1, 3, as in Python. So that's just something worth noting. And now we got to go back to how do I think you should be. Doesn't like that. Okay, maybe I won't try and do this much. First time running through. Oops.
There. I hope. No.
Okay, we're just going to reload the data. Okay, we're good now. So when you have real world data, the first thing you should always do is take a look at it. Does it make sense? What do the variables mean? So we're going to get the data, this Boston data, from a package called mass, and we're going to use summary, which gives you summary information about all the columns, and head, which shows you the first few rows. So summary Boston, I told it instead of import blah, 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 you just go library and it gives it to you. So this is import mass as whatever you want it. And then summary Boston gives you the summary information. So there's a variable called crim, zone, indos, which is how industrial it is. And you can see for every single one of these, it gives you the minimum, the first quartile, the median, the mean, the third, and the max. So it gives you some idea. So, this is the tax rates. And the last one is MEDV, is median value. That's the median value of a home in that zone. And that's what we're going to try and predict. And this slide may be a little small, but you have access to them. You can look. This slide just contains more exact information about what the different variables mean. Now, here's the thing about machine learning. On the one hand, you have to look at the data. You have to be able to make sure there's nothing in there that seems wrong. On the other hand, if you really believe in these ideas, you don't have to be experts in the topic. So I'm just going to skip over that. And as I said, head shows you the first few lines. So this is just something, if you were doing this for real, and you'd want to look at this, just sort of get an idea, what does the data look like? And we can see, the 14 variables.
This is absolutely not politically correct, I have to say.
The data?
Yeah.
What's wrong with it? Oh, the percentage.
The percentage of African Americans. That's okay.
What does it say over here? It says
BK is the proportion of African Americans by town.
Oh well.
Well,
if it works, it works. So as I said, we're interested in not just explanation. We're not interested in describing the data, which is what they wanted to do. We're interested in predicting. So if you want to predict, as Neil said, you want to divide the data into two pieces. A training set, which you're going to use to train your model. Now we're going to do a linear regression. And then a test set to see how well does the model work. And it's very important that you don't cherry pick what's the training and test set. The fact that it's a random selection gives you some comfort that what you see in your training set should work in the test set too. We can, in R, the version of scikit-learn is something called the carrot package, and I will introduce that in following weeks. But for now, we're just going to do this by hand, get our hands a little dirty just to see how these things work. And I'll just use 70% of the data for training and 30% for testing, and that'll be fine, as opposed to the 80-20 that Neil said. It's really not important. So first thing I did is I set a seed. If you're doing things for reproducibility, you want to do this, get the same answers time and time again. It turns out there's no such thing as a random number. If you set the seed to be something specific, you'll get the same set of random numbers over and over again. So that's important. And then all I want to do is randomly take 70% of, well, roughly 70%. So I'm going to take 350. I'm going to sample from 1 to 506 because I have 506 rows. I'm going to take 350 of them randomly. And the way you index in R is I call the Boston.train. I take the Boston set on the training index, and the test is all the things that aren't in the training index. So Boston.test is just Boston on minus train.index. And the comma is important. That tells me that the fact that it's train index comma means I want the rows, and then I'm going to take all the columns. So by leaving a comma and nothing on the other side, I'm taking all the columns. So all I've done is divided my data set of 506 rows into a test set of 156 and a training set of 350. To do regression in R, just like in Python, is pretty easy. The function is called LM. And if you want specific information on your console, you can type $LM. And R is a language actually that was created for statisticians at Bell Labs to use. So it was made to be pretty easy. So here's the syntax we have. It's Boston.model equals LM, and I want to calculate median value, and that tilde dot. So tilde means it's an equation, and the dot means everything else. So what this means is I take every variable in my data set except the median value, and I want to predict median value. And then finally I tell it that the data I want to use to do this is the Boston training set. So this is kind of the heart of how you do this in R. And in R, everything's an object. So I've created an object called Boston.model that has lots of properties. We'll get to that in a second. But once I run this code, I've created an object, and one of the things it's done is it's done all the gradient descent and everything. It's created a model, and it doesn't care how many coefficients, it's given them all. So I think this is all that. Let's see what it actually did. So as I said, it's an object. And one of the properties this object has is a summary function. So if I hit summary, I just want to push this up a bit. It gives me all the information I want. So it tells me, well, first of all, the residuals, the difference between my predictions and the actual values. The median value was minus 0.5, and it ranged from a minimum of minus 10 to a max of 24. And then it gives me a bunch of statistical information. We'll get more into this in later sessions. One of the things that this suggests is that some of the coefficients aren't useful, are not really relevant. Incidentally, this is more politically correct. It suggests that the black coefficient may be useful, but it isn't that useful. These this column says, according to the standard theory, which we don't believe in, of linear regressions, the probability that the real value of these coefficients of 0 is. So when you see 3.7 to the minus 11, it says it's essentially no chance, no probability that that real coefficient should be 0. So without believing, okay, so there's two things. There's regression and there's least squares. We're really doing least squares. We're producing a model whose coefficients are just linear equations. Ordinary least squares says this is really the right model under a number of hypotheses about the data. And the most important one is that each time all the residual terms are independent and they're random noise. In the real world, they aren't. But that doesn't mean it's not a good model. It just means it doesn't have the properties. So if you had fulfilled all the properties of linear regression, this would say that you had a really good model and that it would predict. But it isn't the way it works. So here I've just written in bullet points, traditional statistics make a lot of assumptions about the model. We're not going to, and in fact, if you check them, they wouldn't hold. And the other thing is the traditional linear model is interested in describing the data set you have. We're not. We're machine learners. We're interested in taking a data set and can we use it to predict. We're really interested in if somebody gave us a new zone in Boston, could we predict the median value of a house there? Okay, so let me give you an example where that might be useful. People buy property tax deeds, right? And so you want it, all a city or state will do is will say, here's, we'll just tell you it's in this zone, and that's it. Well, what do you think it's going to be worth? If this model works, you could use this to decide which zones you want to bid in and how much. Okay? So is it? Okay, and I think I've covered the points on here. We really want to see if this model we've produced with Boston with the training data is going to work well with new data. And the first new data we're going to give it is the test data. All right, so we do run into this question of maybe I didn't do so well, but before we go any further, if the model's crappy on the split, it's probably not a good model. So let's see how well it works.
Hey, Adam, I have a question.
Great.
So let's say like of all the independent variables, all the X variables, if few of them are correlated, right? So can you still rely on the significance of the variable at an individual level? Or they can split between the two factors, the loading?
Okay. So Manish is saying, one of the things that can happen is that variables can be highly correlated. Now, in traditional linear regressions, this can be a huge issue. It's an issue we'll deal with. I mean, just because we have 13 variables doesn't mean at the end of the day, we want to make a model with 13 variables. What Niels was hinting at, and what we'll see more in a second, is that less is more. What happens when you produce a model is you give up how accurate it is in describing data to create models that are better at predicting on new data. So if you are just interested in descriptive, in seeing how well to create a model for the 506 zones you had, the answer is no, you leave everything in. And if you're interested in predicting, we'll see next week when we talk about regularization that leaving out highly correlated variables will typically improve predictability. So whether a model will say two highly correlated values have very similar p-values or not is a complicated thing. The problem is it's not robust procedure. And that's one reason why we will use less variables in the end. Does that answer the question?
Yes, thank you.
Okay. So R has a method called predict that makes calculating new values. So here's a quick quiz. first quick quiz. Suppose that the model was perfect, was spot on. For every example that you calculated the prediction, it was exactly the value of the median value of the housing price. And you plotted that, the prediction against the actual. What would that line look like? And here you have a bunch of choices.
It can be, if you want to put some other choice, you can put it on chat.
But let me give you a hint. What this would say is if you were plotting it, that the value of the prediction was the same as the value of the actual value, they'd be the same. So if you predicted 350,000, the actual value was 350,000. If you predicted 198,000, the actual value would be 198,000. Right? So are we ready to close?
Give me 10 more seconds.
Okay.
We are closing in 10 more seconds. Okay.
Okay, Vox Populi, the popular answer was y equals x. And that's correct. You'd have an absolute, just a straight line across. Maybe I should go to the board and do this?
Yeah.
Okay, so I'll go to the board and illustrate this. Sets it up, I'll erase. So looking at the difference between what you predicted and what it is called a scatter plot. It produces scatter plot. Now, what would it mean if this was you always predictions were perfect? Meaning if this was your actual value, you would have predicted the same. Right? So the x value and the y value were here. If you had an actual value out here from your data, the predicted value would be the same. So you would just get the line y equals x. Now, this is a pipe dream. This is never going to happen. But what this means is if I have data like this, your model is doing a pretty good job of predicting. If you have a point, let's say over here, what does this mean? It means your actual y value is small and you're predicting a really large value. It's not a good prediction. So this would be an example of a point where the model didn't work. So the answer is, if your model was perfect, you would just get the line y equals x. Anyone have any questions on that? All right, I'm going to go back. Oops. So here is the actual scatter plot of the predictions versus the actual. So the predictions are just as I drew them on the y-axis. And this actually, to my mind, looks pretty good. You'll notice there are a few points that are way off. Now notice what this corresponds to, houses that are very high priced. It's incidentally a very well-known fact in the housing industry that it's much harder to predict housing prices when the houses are very expensive. But overall, the bulk of the data is like a cloud that kind of looks like a straight 45-degree line. So the model looks like it's not doing so bad. Now remember, this is just on the training data. I mean, excuse me, this is just on one split. Now, and I just want to point out, if you do R, there is this plot function that'll give you 4 plots. but where is it? Having trouble finding the one I want. It does do a QQ plot, which is this one. This is the plot that says, if you look at this, the more that this looks like just a straight line, the better your model is. And this is showing exactly what the scatter plot showed, that it works pretty well, except on the higher price houses, it really doesn't work well. Okay. So one thing we can do is we can, just like Niels did, find out how much on error. So I actually ran code, so I'll explain what this is. But all this is doing the exact same thing Niels did. It's finding the square of the difference between the predicted value and the actual value, summing them up, and taking the average. And so we see that the average is 0.389. Now remember,
you're also taking the square root here. We were taking the squared error. We didn't take the square root.
Okay. So this is what's called the root mean square error, which is a very common thing. So it's saying on average, well, this is kind of the Euclidean distance. So it's saying on average, my prediction was 0.389. So that's $389, right? Because the median value is in thousands of dollars. So it's saying that on average, my prediction was $389 away. That's not so bad. And all I did was I took some...
Except these prices are from 1960 or something.
The prices aren't that high, but we could tell you what they were on average. We have to go way back. But the mean was 22.5.
Yeah, 22,500. Yeah.
So still, the median value was 21,200, and I'm off by about under $400. I think we'd be happy with that in the real world. But you know, the good old days when you could buy a house for $22,000
in Boston.
In Boston. Okay, so here's another quick quiz. And I think I've sort of I've sort of given away B. So is the difference evidence that the model is good? Do you like 0.389? I've kind of said what I've said, but this is just an opinion. Do you think that's good? And I've kind of said, what does 0.389 mean? But I won't repeat it, so you'll have to at least have paid attention. So the first one is just an opinion. And by the way, you know, if in the real world you make a model, the first thing you do is you look at the results and say, what do I think? Does this look good? Well, I think I gave it away. But this is what you do, is you look and you see, is this good? Now, is this the end of the modeling process? No, this is just the start. Tell me when you're ready to close, Manish, and I'll stop chatting. We were talking earlier about the fact, what do you do if you got unlucky? Maybe I cherry-picked the data. How do you know I didn't, behind the scenes, cherry-pick things so it'll look good on the test set? Well, in this case, the way you would know that is it's pretty easy. You have code. I've shown you code. You could go set your seed and see if you got the same results, or at least very similar results up to rounding error.
So, Adam, can you see the results?
Yeah, so the results are pretty conclusive. Everyone agrees that this is evidence that it's a good model. I can't read. Percentage of model variance was the second most popular. Average error, and that is the correct answer. The 0.389 is the average error. Okay? So, can we just cross this out? So, as I was saying, how do you know I'm making this up? And maybe I cherry-picked the data and found the right test split. And this was the question that was asked earlier. How do you know that when you took the split, it didn't buy, or maybe I didn't cherry-pick it, but maybe just by luck, I happened to pick a good split. How do I know that this is? So how would I do that? As I said, did I cherry pick it? Well, you saw it. I took a random split. You can do that yourself. This is reproducible research, as I say. So, and this is a personal point, but one I feel pretty strongly about. When I read a new study shows, and this is a, if you've ever heard of XKCD, this is the reference, jelly beans cause acne, I always say, did they show me the data? And they almost never do. And so I always say, I don't believe it. I have no idea what they did. And it's, you know, there's a lot of evidence that many scientific studies are wrong. But for your own amusement, Google XKCD, do jelly beans cause acne? It's one of the classic cartoons of statistics, if there could be such a thing. Okay, but for number 2, how do I know that this split was good? Here's what we can do. We can go over the entire code again and just pick a different split, right? If I do a different split, I can see if, I mean, I have the code. I can really cut and paste my code. I don't have to do any more work. I can cut and paste the code and do it all over again. You know, the data is already there. I just have to cut and paste the code and see what happens. So here's the code. And there you see I got the same answer because I set the seed at the beginning. So, but we knew that. We knew because I'm just redoing what I did. All this is showing is the exact code I had before, but it's just put in one block. But if you remove set seed, I can put it in a container and just run this over and over again. So this first line is I'm creating a matrix with 500 entries. And I'm calling it error.boot because I want to see what the error is. And now, what's my code? For I equals 1 to 500, so 500 times, I sample from my data set. So what I'm going to do is 500 times, I'm going to create a test and train. So for each I create a training index, which is sample, and divide my data. So I'm creating 500 training sets and 500 testing sets. And for each one of those sets, I now create a model. I see what my predictions are, and I compute that same error. All I've done is I'm indexing by I, in this for I equal 1 to 500, I'm indexing my process 500 times. And it's not like this won't take any time to run. And then I see what the error is, and I put it in the ith spot in the matrix. So after I've run this code, I will have a matrix with 500 numbers representing 500 distinct errors. For 500 times, I created a test set and saw how well, I created a model with the training set and saw how well it did. Now, what's this going to tell me? Assuming the answers are pretty good, it's going to say that this model really works. It's going to really work in the real world for predicting median values of houses in 1960 in Boston, but you know, that's not the idea. So summary is just a function it tells me. So what do I see? I see the average error I get is 0.387, which is awfully close to the 0.389. And what's the range? They range, well, I have a pretty big outlier of 0.53, but that's still $530. I did this model 500 times, and the worst error I got was $530. The best error was $300. And this is, so what this means, and this was on data it hadn't seen. This to me now is going back to the question that was asked of Niels. This is really pretty conclusive error that this is a good model. If you want to predict the median value of houses in 1960 in Boston by zone, this model will work. Okay? It wasn't just random luck that based on the test train split that it worked. It just works. Now, again, in a future lecture, we're going to discuss this in greater detail, but this is called bootstrapping, in essence. This is a form of bootstrapping. And the idea of bootstrapping is that you have data, you can continually reuse it, and you can get more information out of it than just using it once. But here we go. This is what you do in the real world, by the way. If you want to produce a model, you're not necessarily so concerned of should the coefficient of the third value be 0.42 or should it be 0.40? You're really concerned, should that be a coefficient at all? Is this model a reasonable kind of model? Anyway, for this case, I claim I've given you pretty good evidence that the linear model will work pretty well. Okay, so another quiz. what does that tell us? Was the original error of 395 good? And the second question, if one was interested in predicting, I can't see, I have to move this, and needed to be accurate within $500, would you trust this model? So if somebody said to you, all right, I have another 500 zones, I want you to produce a model with them, would you feel, and they said, I need this model to be within $500, would you think that was good? Would you think you were likely to do that? Okay. So we have 100% so far of yes was the original error of 0.395 good, and 100% of yes that if one was interested in predicting median value needed to be accurate in $500, is this a good model? Why? Well, we saw, we tried it 500 times, and the worst error we got was $500. Does that prove that if we do it the 501st time, the error won't be $600? No. But it does provide some damn good evidence. And that's all a model can do, because we're talking statistics here. We're making predictions. We're not creating causal models. So just to chat for a second, the first evidence that cigarette smoking causes cancer came from a study, I think in the 1930s in Britain. And they did a simple chi-square test, which examines whether it was likely that the rate of cancer patients in people who smoked was the same as the rate of cancer patients who didn't smoke. And it produced a model which said no. It did not prove cigarette smoking caused cancer. It suggested it. And it allowed doctors to then go on and find out that in fact it did. So, you know, you have to be careful what you're doing. We're not proving that this model has under $500 error, but we're saying it's awfully likely. And it's, you know, it's an old quote that I think actually is originally from Ecclesiastes, but I heard it from Dashiell Hammett. And he said, the race doesn't always go to the swiftest nor the fight to the strongest, but that's the way to bet it. That's where we're at.
So Professor, I have a question. So then is cross-validation and bootstrapping the same thing, or they are different?
No, they're different. Cross-validation is you divide your data set into a number of pieces and use all the pieces but one to train a model and see how it works on the last piece. So if you do five-fold cross-validation, you're dividing this data into 5 pieces. So this one on bootstrapping is sort of like it, but it's a little more sophisticated. And when we talk about bootstrapping, I don't know, week 2 or 3, maybe I think week 3 more, it's a much more robust procedure than cross-validation. A lot of times cross-validation is used when you don't have enough data. A lot of times cross-validation is used in sort of an intermediate step when you need to reuse the data and you can't use the test set.
Yeah. So this is like using the train test split many times over.
Sure.
So at each time you do the train test split, it selects a new random test set.
So in general, if you have enough data, you divide your data into a training set and a test set. Cross-validation is more useful in situations where you don't have enough data. Now, I could have used cross-validation inside each loop to find a better model, but you know that's a bit of overkill. But in general, if you have enough data to do train and test, you don't worry about cross-validation. But you know, when you're building big, complicated models where you have to, you know, somewhere along the line see does it look good, then you would see if it's looking good. Then you would use cross-validation to get an idea of how well the model's estimating.
Thank you.
So a few more points. I call this bootstrapping, and it is, but usually with bootstrapping, the issue is you want to figure out, as I say, you bootstrap with a replacement. In this case, I didn't. There was enough data, and the point I was trying to make was a little different. But bootstrapping, when you use it as a technique, you're usually trying to say, to make more complicated estimates in which you need to reuse the data and over again. When you use it this way, it's a fantastically useful thing. So when, I have so little value, I put personally so little value in it, I won't even bother to go back to the page. But in the page where they had the linear model, it gave you all sorts of estimates. It not only gave you values for the coefficients, it gave you estimates for how likely they were to be, actually zero. It also gave you confidence intervals. I think one of the real weaknesses of the standard model is those confidence intervals are just way wrong. And with bootstrapping, you will see you can use it to produce really much better confidence intervals. So in other words, I tell you, so when we did the test once, I said the average error was $350, say. You could say to me, well, do you really believe that? Is that really logical? Is it reasonable? How accurate is that be? If I give you new data, is it going to be around $350, or is there some chance it's going to be $800 on average? And the answer to that had to be, I don't know. But after we did the bootstrapping, then I could say, yeah, I'm pretty confident. Your chances are, if you do this, you're not going to have an average error of over $500 per house. Okay? So bootstrapping will allow you to get not only coefficients that are pretty accurate, but allow you to get confidence intervals. And that's a really thing, where because you can then just say, I predict it's going to be this, but you can say, I predict it'll be this, and I feel confident enough on this, I'll bet $1,000 on this. Or I predict it's going to be this, but if you want me to bet more than $5, no thank you. So it's a very important technique.
Okay. Adam, I've got a question. So Neil's got the Jupyter notebook up there where people can practice. Is there something or some assignment or some section of the code which people who are interested in writing in R should be practicing? If you can.
What I can do is I just uploaded the HTML document. I can upload, the equivalent of an IPYNB file is what's called a .rmd file. Mm-hmm. And I can upload the .rmd, which anyone who has has R Studio can open, and they can play with the code. The code is there. It's as code. They can run it. They can change it. They do whatever they want. So I'm sorry. I should have given you that one too. I just forgot. Okay, that's great. So what I'm going to do is I'm going to send the link or upload the link of your tutorial or the lecture where you talked about installing RStudio, so people have understanding of how to install RStudio, and then you can upload the RMD file, which they can. I will do that. Though, I mean, between you, me, the wall, and everyone else who's in this room, installing R and RStudio is, at least on Windows machines and in the cases of Mac I've seen, is a very, very straightforward project. You go, you Google R, install. It takes you to CRAN. You install R on your machine. It's 2 or 3, clicking of yes, and then you Google install RStudio. It takes you to the RStudio website. You pick your operating system. It's pretty straightforward. But so for that, it's fine. But I believe also in that talk or the next talk, I talk a little bit about basic usages, how you can use RStudio and some basic functions. So if this R stuff appeals to you, but you're not quite that familiar with it, there's some information about basic R coding. Okay, and other question, is there any textbook people should be following?
No.
For better or worse, this is all out of our heads.
Okay, sure. Okay, so probably we can ask, like, if anyone has any questions, they can ask right now, or later they can put it on discussion board, or they can email. But feel free to ask questions. We can have 5 minutes for questions for this session. Tejas, Avinash, Vijay, a lot of people. I don't know many of them, so you can introduce yourself and ask question. Anyone?
When is the homework due by next week? The one that Professor
we'll give you 2 weeks
2 weeks.
Okay. Good. Okay. And that's also posted on the website. Yeah, I haven't seen it.
It's in my notes on the last.
Okay.
Which is on the website, I believe.
Yeah, that's on the those.
I just have one comment about like testing and training sets. Probably the way we do the random split, probably, I mean, Adam and Niels, you can comment on this because you do it all the time. It may not be the best way to do it for the financial time series because there's learning on the data. So the later data, which is later in the time series, has some knowledge of what's happening before, what happened in the past. So if we randomly just split test and train, there may be some bias.
That's a good point. That's a good point. You don't want to do this for time series data. Yeah. You don't want to do it like that for time.
Not that simple. You have to make sure that you split in time too. That you train on time only on information that isn't available, later on. Right. So you train on 1996 and you test on 1997. You train on 2017, you test on 2018.
Right.
So but that's special to, but it's a funny thing because that has to do in a funny way. You are randomly selecting the data, but just the structure of the data is different because you have this time component, which is different. There's an ordering to the data. If you think about it, all, the Niels example, my example, if you rearrange the order of the data, it meant nothing. I mean, if you change the order of the rows, it changes nothing. Whereas for time series, it really does.
Yeah, it's
we can remember the past, not the future.
I mean, this is not really for time series data in the sense that you can't regress over time. So it's you need different models for time series. So there you need like auto-regressive models and stuff like that. But you do need different models for time series. So you will not use linear regression for time series data.
Any other? Yeah. Any other question? Otherwise, we'll end the meeting. Okay, thank you, Niels. Thank you, Adam, for this very wonderful class. Vijay, you have any comment? You have any questions? Vijay always has some question.
No, I think I thought it was great. Just a quick question first, Niels and Adam, are you planning to talk about time series or we're just doing multidimensional data and different models for that?
No, I don't think we're planning on doing time series data in this. I mean, the model the machine learning models you use for time series are probably a little beyond this course here, but maybe in a later course. But I don't think it's really. I don't think we're going to do it here.
Yes, I agree with you. It tends to be very specialized to talk about time series. And there's plenty to cover with these multidimensional data sets anyway. So just quick question here. Now, I mean, by the end of this lecture, we have covered multidimensional linear regression.
Uh-huh.
Are we going to, in the next session, are we going to talk more about generalized linear models and just stay in the space of linear regression, or are we moving to other types of models?
Next lecture, we're planning on doing logistic regression and classification.
Which is a generalized linear model.
That is a generalized linear model. But
yes,
very special generalized linear model.
Yes.
So we're going to classification. I mean, I think most of the course will be about classification.
Okay.
Wonderful. Wonderful.
And after we do that, we're going to spend some time talking about producing models, how you produce the variables you want. As Manish was saying, if you have highly correlated variables, this can lead to issues with producing models. And we're going to not only continue discussing, how you sort of make sure you believe your model is a good model, but we're also going to discuss how you add into the mix variable selection. Maybe you only want to use 5 models of the 13 in this, and you may end up with better predictions if you take the right 5 variables, and we'll talk about how that comes about and why.
So we'll spend some time on quote-unquote feature selection or variable
Absolutely.
selection.
No. So,
just one more quick question. I mean, maybe this is mildly technical, but typically when you approach linear regression, one of the measurements of how good the model is the use of R-squared. And I noticed you specifically didn't invoke R-squared in this conversation. We constructed our own error measure, square root error measure.
I mean, R-squared is a measure of how well it fits on the training set, right? So that's not what we're so interested in.
And in fact, I'll make an even stronger statement. R-squared, you can always get R-squared as good as you want by adding more variables.
Yes.
You can add noise. You can add things that you know have absolutely nothing to do with the behavior you're trying to model. And R-squared can't go down. It always goes up. However, when you add more variables, what happens is that while R-squared goes up, the predictive power of the model goes down. So R-squared is a very poor measure of predictive abilities of models. And in fact, in almost any situation, we'll see when we get into this, when we talk about regularized regression and feature selection, we'll see that the ordinary least square model almost never is going to be the best at predicting. So it's, for our class, R-squared is not a particularly interesting number.
So the mean square error or the root mean square error is what we should.
Well, on the test set, on the test set, it's important. So I mean, there are 2 things that you, when you do a machine learning model, you have what's called the bias, and you're going to have the variance. The bias is how well it fits the training data, and the variance is how well it predicts or how well it fits on the test set. And those 2 things are they're not mutually exclusive, but you try to find something that is reasonably well on both the bias and the. But you can't. You are mostly interested in the variance. I mean, you have a model that fits terribly on the training set, but predicts very well. That would be a very rare situation, I think. That's what you would be interested in.
The famous bias variance trade-off, right?
What's that?
Bias variance trade-off. And I'll give it. This is something where we have a respectful disagreement. No fisticuffs yet. I'll give a different view on bias variance, and how you interpret them. But you might have, when I computed those error terms, the RMS, the root mean square errors, I only did it with the test set. Had I done it for the training set, as Neil said, inevitably it would have been lower, but I didn't do it because in some sense, who cares? We're interested in predicting. And, we wanted to see how well it predict. And incidentally, the fact that I did it 500 times and every time it predicted pretty well is evidence that this is a good model for prediction. Now, as we said, I could have added, the price of tea in China as a variable, and it would have improved R-squared. It would have thrown the, predictions way out of whack. And one of the popular terms for this is that, it's called literally modeling the noise. You can't have the model that fits the data that you create the model too well, because you don't want it to follow every nook and cranny of, data, the idiosyncratic behavior.
I mean, you can find a very high dimension, a high degree polynomial that will go through
every data point.
What's that?
A high degree polynomial that will go through every data point.
Yeah, right. But that would be horrible at predicting, right? So you would have a 0 bias, but terrible variance.
Yes.
And as I said, with random noise, you probably can't get 100%, but you get like R-squared 99.9. You could get grade R squared by just adding noise variables, but then the predictions are gonna.
Yes, and I asked that question to highlight the care you have taken to delineate R squared versus mean square error or root mean square error. Yeah.
I'm sorry if I gave R squared short shrift and poo-pooing.
No, I think it's good. I think it's very important for those who are new to trying to figure out what is the right measure for goodness of a model.
Yeah.
Many discussions that suggest something to do with R squared is helpful and creates confusion. So this is probably very important.
Yeah, well, I mean, again, it depends on what you want to use the model for. You want to use the model to sort of study causality, or how much does a given factor affect the output. Then of course, R squared is somewhat useful in the sense that you want a model that fits your data as well as possible in order to, you want to estimate how much does a certain factor, how much does it affect the output, how important is it, right? But for I mean that for prediction or for machine learners, it's not important, because we only care about what it does when they see something new.
Yes.
What it does there.
Well, I would point out, if somebody produced a model, an econometric model on a data set, and said, you see, this proves it, and they gave it new data and it didn't work, I would say, you see, this disproves it.
Right. There's a question someone is asking, what are the, can you please let me know what are the prereqs to understand these sessions very well? And also, are there any online MOOCs for understanding the prereqs? I think I would say like some basic statistics, matrix, linear algebra, and calculus. What do you think, Adam, Niels?
Yeah,
Agreed. And for basic statistics, we do have the acas.org class for that. That is online.
Yeah.
Linear algebra, I'm sure there are very good online, resources. I'm just not familiar with them.
Right.
Yeah, I mean, it's going to be very difficult if you don't have at least a little bit of, if you need to know what a matrix is, you need to know what
how to take an inverse of a matrix, of multiply matrix. You
need to know what it means. I mean, you don't need to know how to do it, because a computer can do it for you, but you need to know what it means. You need to know what it means to multiply two matrices together. You need to know what it means to take partial derivatives of a function.
Yeah. Okay.
In some sense, Niels' lecture, showed all this because he was taking vectors, so there was linear algebra, and he was taking vectors of partial derivatives, so there's your calculus.
Right.
Yeah, I think that is a prereq for.
Yeah.
We'll try to keep the math down, but there's going to be some.
Yeah, no, I think this was right level, because we just don't want to dilute the course and make it like any other course. We just want this for serious learners, where they get like a right balance of mathematics, the foundation, as well as the examples how to use it. I guess that's the idea when we came up with this course.
Yeah, I think so too. I mean, I think it is. I mean, it's not. I mean, if you're just going to use a canned function to do everything without knowing what goes into it, what really is, then it's not really a good thing to use it in practice, because if you don't know what goes on and what you're doing, then you are very likely to make some serious mistakes.
Right.
So.
Yeah, I've seen some examples where people create like a Sharpe ratio of 15. And then out of sample, it's like 0.2 or negative.
Yeah, right. Except when it comes to real money, it's not 15.
All right.
Just one, Adam. What was the quote that you had mentioned about? That's the way I'll bet it.
Oh, you always. It's not always the swift who wins and the strongest who wins. What was that, Adam? But you bet on those.
So I read this in a novel by Dashiell Hammett, but looking it up once it came up, you can find it somewhere in one of his novels, but the essential quote is from Ecclesiastes, and it says the fight doesn't go to the strongest, the fight doesn't always go to the strongest, nor the race to the swiftest, but that's the way to bet it.
Wonderful. Thank you.
All right. Thank you, everyone. We'll end the lecture here.
All right.
Thank you, Neil. Thank
Thank
you.
you.
It was great.
Thanks a lot. Thank you.
Next week, and feel free to send emails if you have questions.
Absolutely.
We'll do our best, but we can't tell you.
Yeah.
Okay.
Thank you very much.
All right. Thanks.
Good night, everyone.
Bye-bye. Good morning.
Good morning.